Hello, you absolute legends. We're going to talk about an example of freezing point depression of solutions. Freezing point depression is a fascinating property of solutions because it does not depend on the identity of the molecule, it depends on the quantity of the molecule. So often in chemistry, when we talk about what is the freezing point or boiling point of a substance, it's like, well, what atoms are there? How are they bonded? It doesn't, let me just say it simpler. A gold coin or a bar of gold both melt at the same temperature. The amount is inconsequential to the melting point. For collagetive properties, the amount does matter. So when we mix a solution of benzene, a liquid solution of an organic compound, 10 grams, and add 1 gram of an unknown, the freezing point is going to depress or go down based on the quantity, not on the identity, the unknown thing. And the freezing point is going to go down at a linear rate. It's going to go out at a rate that has a funny number and unit to it. But the freezing point is going to decrease at the slope, this is really the slope of the line of how many degrees the solution of benzene will decrease based on the molality. This is a number we look up in a textbook. Molality is a terrible unit, but let's just leave that as it is right there. Let's think about our atomic vision picture and what's going on and what we will do in the lab, hypothetically, before we do any more of the scaffolding or numbers. So we have the 1 gram of the unknown compound, just with these red circles here, and we have a liquid hydrocarbon solution, and I don't have a blue line here because it's not water. This covalent compound, these molecules are going to spread out evenly within the solution. They're going to move in straight lines until the other lines collide with another molecule at the edge of the container. There's going to be like a huggy bear of benzene molecules doing some sort of interaction between them for them to be and remain in solution here. Every solution is going to have a freezing point. I say every, but not all of them. Most of them. Every solution, its freezing point is going to go down based on how much of this unknown is in there. So freezing point of pure crystal, pure benzene is 5.5 degrees Celsius. That is pure benzene. And we know that the freezing point is going to go down just because that there's other stuff in there. Now, whether it goes down a little bit or a lot depends on how much is in here. The more that's in here, the more it's going to go down. In this example, in the laboratory, it goes down 1.9 degrees Celsius, and what you observed in the lab was 3.6 degrees Celsius. So let me just kind of clean up my board here. You observe this freezing point, pretty simple. You really just, like in the laboratory, you would just get a -20 fridge, -20 freezer, or you just put a thermometer in there, and you just open the fridge door every 5 minutes and see if it's frozen. Whenever it's frozen, you look at the temperature, and then you kind of do little things to narrow it down. But this is what you look up in a textbook and say, look, pure benzene is going to freeze at 5.5. This solution froze at 3.6. That's a 1.9 degree drop. Okay? Now, for every 1.9 degrees this thing drops, that tells us how much is in here. Let's talk about the calculation and how we use this constant here, okay? At the end of the day, we are trying to find our final answer in the unit of grams per mole of our unknown. I should state that very clearly. I haven't yet. This is how I want my final answer. This unknown sweetener, what are the grams per mole of the sweetener right here? I have the grams of it. Yes, that's a gimme. I got that. Moles. This is where this linear constant of, the freezing point depression constant of benzene, where these ugly units need to be kind of prettied up and dolled up. Molality is moles per kilograms of solvent. So let's stretch this out. Moles I hope you can read my hand right there. Moles of solute times kilogram of solvent. So here, we want to get our final answer with grams of solute divided by moles of solute. So we need we need moles in the denominator and grams on top. Let's set up our scaffold. We want grams on top, so let's just plug that in right away. 1 gram, and that is of our sweetener. I'm just going to put down UNK, UNK for unknown sweetener. I need moles in the denominator, so I'm going to put this in the second spot right here. Now, what I've done is what I call the smart start, and I am using the words, the units, to guide my placement. This is what I need my scaffold to look like at the end of the day. Grams on top, moles on the bottom. So I'm just starting with that right there. Grams on top, moles on the bottom. Now my task has turned to canceling these units out. I need to cancel out degrees Celsius. And I have the degrees Celsius that the freezing point was depressed by, the experimentally observed number. Now that unit's canceled. The kilograms of solvent. 10 grams of benzene is our solvent. So just to do that in kilograms, that's not going to cancel. I'm out of board. I wrote that up there because I was out of board, but a side doesn't cancel outside. That would not work. Squeeze it in there, apologies. But now that cancels. We had a little bit of an atomic vision and a problem. We have an unknown sweetener and we can find the molecular weight of the sweetener. The only units that are not canceled out. This scaffold will tell us the molecular weight of the unknown sweetener. Bonus points. Can you identify Google and try to make a guess of what that artificial sweetener is? Maybe 1 or 2 guesses. Hope this helps. Thank you.